Okay, so I want to talk about an old exam question that from 1819 fall. Here it is, 1819 fall, exam 3. And specifically, we're going to go over and look at question 2. So let's see. In fact, let me do it like this. So the start of this question is actually pretty straightforward. We notice first the question asks us to diagonalize, right? So we're looking for this diagonal matrix E, right? And an invertible matrix M by which we conjugate, right? You can see that this is a conjugation right there. So this is a diagonalization question, and we know from the notes that the way we diagonalize a matrix, right, is by finding the eigenvectors and the eigenvalues, right? So the eigenvectors are going to tell us the matrix by which we conjugate, and the eigenvalues are going to give us the resulting diagonal matrix. Okay, so the algebra, of course, right here. All right, so that said, eigenvectors and eigenvalues, no big deal. We take this matrix and find the characteristic polynomial, straight up algebra. We factor it, write down the roots. Of course, the roots are the eigenvalues. Okay, and then we find the eigenvectors, and this is also a pretty straightforward process for each one of these eigenvalues. Right, we plug in, we write down A minus lambda I. This gives us a singular matrix, and then we find the null space. And you could row reduce if you like, but recall from the lecture, I think it's very nice in many cases, especially with these small 2x2, even 3x3 matrices, to make a rank argument, right? It's pretty easy to observe that these rows are multiples of each other. So the rank is obviously 1. Right? And once you know what the rank is, that means you also know that the dimension of the null space is 2 minus 1. And that right there is a huge amount of information. This tells you that there's really only one eigenvector to be looking for. And once you know there's only one to be found, a little bit of trial and error can confirm orthogonality to the rows and thus that this is a null space vector, aka eigenvector. Okay, so likewise down here. So we have the eigenvalues, we have the eigenvectors, and here's where a lot of students will make a mistake. A lot of students will say, okay, well, we found our basis of eigenvectors, and recall from the notes, the eigenvectors that makes up the columns of the matrix. And so a lot of students at this point would say, well, then this matrix, the matrix by which we conjugate has those columns, and write it down and walk away. And that's wrong. You have to be careful and make sure that the matrix that you're looking for is actually this one and not that one. How do you know, right? Do you want the matrix do you want the matrix whose columns are the eigenvectors, or do you want the inverse of that, right? And it really could go either way. It's the question will not always come to you asking for, between the two of these matrices, the one that is the easiest to compute. And if you think through the specifics of this circumstance, so here we're conjugating a diagonal matrix to get the original matrix, writing that down. Here's our original matrix that, typically we would have called A. Here I'm conjugating the diagonal matrix that I typically would have called D. Of course, we gave these different names. And this is all with respect to the script V basis. So those bases have to fit like that. And this is all with respect to the script S basis. So that means that these bases have to go like that. And so you see, yes, we do have a conjugation, and yes, these are inverses of each other. But the one whose columns are the eigenvectors is the one on the left, and the one on the left is not the matrix I've been asked to compute. right? I've been asked to compute M. M is the one on the right. It's the one that's, it's not the one whose columns are the eigenvectors. It's the inverse of that matrix, right? So you've just got to be a little bit heads up on questions like this. Make sure that of course, you've heard me say this in the recordings many, many times. I am a big fan of don't just call these matrices here, P and P inverse, and just sort of be blind to the bases, right? And assume that, well, it's always going to work out the way we want it to work out. Really not, right? So always, unless the circumstance is already established and clear, when you are not sure for sure which way it's going, indicate these matrices with the bases visible, and make sure you fit the pieces together in the way that they have to fit, and then interpret from that which one's the one you want, or which way does it have to go, what have you. That all depends on the circumstance. Okay, so last very quick comment on this. I want to point out some students might interpret this as a trick question, and I think that's important to address, that this is not a trick question. This is a question that doesn't just lend itself to an algorithm, to a plug and chug process, right? But trick questions suggest that the question is deliberately trying to catch the student on a point of triviality that's not important. That is absolutely not what's going on here, right? This point of issue that these matrices are sort of, if you will, written in the wrong order, the inconvenient order. That's how questions like this will come. And applications, in a real world application, when you want to find a matrix that is conjugate, let me come back up here, that is conjugate in some way to the original matrix, this way might be dictated by the context. The context is what's going to tell you whether you're going to need M to be on the right or on the left. And that context is unconcerned with what might be convenient, right? And which way is going to be the easiest one to work out. So this is not a random trick that's irrelevant. No, this is a worry that 50-50 will come up in any real world context. So you've really got to think it through, or half the time you do these kinds of questions in the real world, you get it wrong. And of course that's bad. Okay, so I think this is a very instructive question. The moral being, again, always think about these matrices by which you're conjugating with the bases indicated visible, and be thinking about those bases as you solve the problem. Okay, so I think this is a nice example, and I hope this discussion's been useful.